Hello friends, we are going to see how do we represent irrational numbers on a number line in this session. So we are first going to talk about representing non-recurring, non-terminating decimal number form of irrational numbers. So now first of all, it's important to understand that each real number can be represented by a unique point on a number line. So irrational numbers, again being a type of real number, can be represented on a number line by a unique point. When we represent a rational number on a number line, we do it by inserting some rational numbers between two integers. Now supposing we make this number line, so we have a 0 here and we have 1, 2, 3 and so on, and on the other side we have -1, -2 and so on. So now supposing we have to represent a 1 by 4. So we know that it lies between 0 and 1. So we divide this part of the number line into 4 equal parts, and then we say this point refers to 1 by 4. So now if instead of 1 by 4 we have to represent 1 by 8. So we will zoom into this part which is between 0 and 1 by 4. We'll magnify that part and then we'll further divide it into two parts and mark the point 1 by 8. So this is how we normally represent any rational number. We insert some rational numbers between two integers, and if the rational number requires so, we magnify that part and then again divide that into some more rational numbers. So as we said, we can insert multiple decimal numbers between two given decimal numbers. So we are saying if between 1 by 4 and 1 by 2, we need to insert 5 different rational numbers. So we can again magnify that part of the number line and then we can divide it into as many, we can make as many divisions as we want into in that section of the number line. So now, if we're talking about decimal numbers, so if you're saying we have a number line from 0, 1, 2, so we can divide it into 0.1, 0.2 and so on. We can make 10 divisions between 0 and 1 with precision of 1 decimal point. Now if we need to mark 0.25, so between the 0.2 and 0.3 divisions we can magnify it and we can make further 10 divisions and then we can mark 0.25 there. So we use the process of successive magnification to represent a decimal number. Now same is what we'll need to do for a non-recurring, non-terminating decimal number. First of all, we'll need to see how many decimal points do we want to show on a number line. So if we take something of the type, say for example we take a number of the type 2.34562 and so on. So we have something like this. Now we can say that if we want to place this up to 3 decimal points, so we can do a magnification after this second division between 2 and 3, we can magnify it and we can then find out 0.3, and then between 0.3, 2.3 and 2.4, we'll still magnify it further and then we'll make again 10 divisions, we'll find 0.34 in there, and then we continue with that process of successive magnification, and that number can be represented as a unique point on a number line. So we can keep increasing the precision to represent the given irrational number till the required precision. So we just talked about representing the non-recurring, non-terminating decimal numbers. on the number line. So now we'll take up another form of irrational number, which is non-perfect square roots of positive integers. So now let's take an example. We need to represent square root of 2 on the number line. So now by Pythagoras theorem, we know that the hypotenuse square is equal to the base square plus height square in case of a triangle, which is a right angled triangle. So if we take this triangle, we know that this is the base and this is the height. So we can say the hypotenuse square is equal to base square plus height square. So in this way, we can say root 2 is the hypotenuse of a right angle triangle with base equal to 1 and height equal to 1. So using the Pythagoras theorem, we know that the square of this hypotenuse is 1 square plus 1 square, which is 2. So the hypotenuse becomes square root of 2. So this is what we are going to use. So now what we do is we take a number line . So we have a standard number line. Now in this case, we take this 0 point and the 1 point of the number line. We mark, say for example, we call this A and we call this O. Now, so this becomes 0 to 1. This is 1 and this becomes the base of the triangle. So at A, we draw a perpendicular of dimension 1. This becomes the height of the triangle. Now this point we mark as B, and if we join the point A and B, this becomes root 2. So we created this dimension of this line segment of root 2. Now we can say that this is not showing it on the number line because the number line is this horizontal line, but we are showing it and at a tilt. So what do? Is we take O as the center and OB as the radius, because we know OB is equal to root 2, and then we draw an arc like this. So this point where it cuts, we'll name it C, gives us, the point is such that OC is equal to root 2. So we've represented root 2 on the number line. Now if we were to represent a 3, we know 3 can be written as 2 square root 2 square plus 1 square square root. So we are saying if we have a triangle with the base of root 2 and height 1, then its hypotenuse would be 3. So what we can do is, with OB as the base, and we draw a perpendicular here, we name it D of height 1, and then this point OD will become root 3. So we can make, similarly we can represent non-perfect square roots on the number line. So again we take OD as the radius and we draw an arc over here, and this will be less than 2. So this point that we get over here, maybe we can call it E. OE will become root 3. So we continue with the non-perfect square roots of positive integers. How do we represent them on the number line? So we've just seen that we could put square root of 2, square root of 3, we could represent all of them on the number line. So similarly, in the same way as we did for root 3, we can represent root n for all possible values of n after representing root n minus 1. So we are saying when we are able to represent root n minus 1, we can take that as the base and we can draw a perpendicular of height 1 and then join those 2 points. The hypotenuse of that triangle will become square root of n. So same way as we did for square root of 3 when we knew the square root of 2. So with that as the base and 1 as the height, we can draw root n. Now there could be another alternate approach of doing that. Supposing we want to represent root 5 on the number line. So instead of taking the step from 2 to 3, 3 to 4 and then 5, we could directly represent root 5 as square of 2 plus square of 1 whole square root. So again using the Pythagoras theorem here. So now what we do differently is, instead of starting from root 2, root 3, root 4 and root 5, on the number line we directly take the point A as this point 2. So we are saying now we have OA which is equal to 2, and at point 2 we draw a perpendicular of height 1, and then this point that we get B we join with O, and this is directly root 5. And now with OB as radius, if we draw the arc cutting the number line at this point C, we get OC equal to root 5. So we have to realistically see which is the better approach of representing the non-perfect square roots on a number line. Now again, root 5 could have been done starting from 1. So we first do a root 2, then root 3, then root 4 and then root 5. But this is a quicker approach to getting the same on the number line.
Friends, I hope you enjoyed the session. If you find it useful, please like it and share it with your friends. You can visit us at our Cool Smart Learning website and post your queries there. And please subscribe to the Cool Smart Learning channel for getting updates on the new sessions. Thank you.